True, false. True, false. Cauchy was the first to define rigorously a definite integral. I think that's true.
Is this posted online?
Yes, sir. You want this one?
Yes.
I'll give you this one after I mark it up.
Again,
All right. Every Cauchy integral is also a Riemann integral. Sure, because the Cauchy tags are just the left endpoints, and the Riemann tags are any points in the subintervals. If a function is Riemann integrable, it is Cauchy integrable. Well, the way it is in the book now, the fundamental theorem of calculus, Cauchy style and Riemann style, both agree on continuous functions. So superficially, that one's true.
couldn't you take any particular partition for your Riemann integral and define a finer partition so that all your heights of the rectangles are on the left end of the rectangles from the finer mesh? Get your Cauchy.
So that would be a strategy. So you have a Riemann partition, tag points. And then what you want to do is make all the tag points part of the new partition. So you take the old tag points and the new tag points and make that a Cauchy integral. Yeah, I think I would try something. I think it is true. The 72. That's, yeah, I know. Yeah, but look for a. That's definitional.
Are there any functions that are one that are just not Cauchy?
Yeah, try to find one. Continuous almost everywhere. I'm not sure that the Cauchy integral can't be expanded a little bit for the ones that are continuous almost everywhere, just like the Riemann integral. The theorem in the book doesn't go that far. It does for the Riemann integral because Lebesgue proved that it's continuous almost everywhere. In other words, the set upon which the discontinuities occur has measure 0. Then you can do the Riemann integral. In other words, it doesn't matter because the total length of the subintervals that contain the pathologies is arbitrarily small. Okay, that's true if you have a bounded function and then the discontinuities are contained in a set of measures, then the thing is Riemann, and it's continuous other than that. Then it's Riemann integral. And that's stronger than being continuous. You're allowed to be discontinuous almost everywhere. Of course, with the Cauchy integral, remember, it could be discontinuous at a finite number of points. If you have jump discontinuities at a finite number of points, you just stop and start the Cauchy integral. So the theorem as it's stated is not as general as it might be. I'm looking for a function that is strictly Riemann integrable and not Cauchy. So far, I haven't found it.
I think, I was just going by.
Yeah, I've seen the same thing in the book. Yeah, that's great. Is it really true, or is it because he has chosen not to? I mean, if he stopped where he did with the Cauchy integral because Cauchy stopped there, okay, fine. But I think you can go a little bit further. You can certainly add finite numbers of jump discount.
I think it was that also, one that said it always had to be continuous. When the Riemann was almost everywhere. I got that almost everywhere, and that would exclude in some cases, but I didn't know that case. So what do you want us to say?
I think I would say yes.
True.
Maybe what I'll do in the interest of clarity is not have any question. Certainly the other way around is true, isn't it? Because a Cauchy partition is always agreed.
Yeah.
Every definite integral can be evaluated by finding an antiderivative.
How about
Are there continuous functions Yeah, that's the one. In fact, I posted something about the Cauchy integral one, and I used that even minus x squared as an example. It's certainly Cauchy integral because it's continuous on 0, 1, but there's no antiderivative. So false. The antiderivative might not be there. If you want to be even weirder about it, the Lagrange function is continuous, so it's Cauchy integral, but heaven only knows what the antiderivative of that is. Tag points define partitions in the Riemann image. False. Tag points define partitions in the Cauchy integral. True. That's probably why it's not there. A tag partition is a set of points that define subintervals of an interval of integration. No, it's the division points and the tag points together is a tag partition. In fact, when we study the Riemann partitions, it consists of pairs. There's a division points, and then they set up the subintervals, and there's a point in every subinterval. So that's good. Partitions are always finite sets.
N, but N is extremely large.
It's finite.
You tell me that's true.
Big.
N is big.
Big is still not.
Okay. I know, because it's far to go to infinity from a billion as there is from 0.
Yeah. That is true. A continuous function on a compact set is uniformly continuous. Whose theorem is that? Heine's. H-E-I-N-E. Heine.
What's nonsense?
The norm of a partition is the length of the shortest subinterval. You wouldn't fall for it. Yeah, I know. The function f of x equals x sine 1 over x. If x is not 0, then f equals 0 is continuous everywhere. I would say so. Why?
F 0 equals 0.
What's the limit from either the right or left as you go to 0? Sine of 1 over x is bounded and x is headed up to 0, so you can make an argument for tension. You can give it any epsilon, you can make that thing as close to 0 as you want. And since it's defined to be 0 at 0, that's good, and that makes it continuous there. Functions defined and equals the two lateral limits. People classify discontinuities two ways. They have continuities of the first kind and continuities of the second. Discontinuities of the first kind, discontinuities of the second. Discontinuities of the first happen when the lateral limits exist and either aren't equal to one another or aren't equal to the value of the function there. Function value exists, lateral limits are not the same, or the lateral limits can be the same, but they don't equal the function value. So removable and jump discontinuities will satisfy that. Would be in that category. Other discontinuities, becoming unbounded, say asymptotically somewhere, one of those things. Those are discontinuities of a more serious type, I guess, and those are discontinuities of the second. All others are of the second. Of the first kind, removable and jump. But controlled by that definition. Lateral limits, function must be defined, limits must be defined from either side. Two things can happen. Either the two laterals are not the same, or they are, and they're not equal to the